In this video, we're going to talk about the time-dependent deformation of polymers. In the case of polymers, often room temperature actually counts as high temperature, and so thermally activated processes are at work during elastic and plastic deformation. So often polymers demonstrate both viscoelastic and viscoplastic deformation. And so we will look at, in what follows, primarily at the viscoelastic behavior and see how the elastic deformation depends on time. So let's start with the case of constant stress, and let's assume that at some time we instantaneously apply a constant value of stress to our material. So just like this, at some time, we'll say t equals 0, we go ahead and apply a constant stress and we just hold it. Now, in other crystalline materials, so long as this stress was below the yield strength, then the material would have some essentially instantaneous elastic deformation, and that elastic deformation would be unchanging in time, assuming the temperature were low enough. It's not the case, though, in polymers, where we observe some strain that is a function of time. So the strain is changing in time. Let's take a look at what that looks like. So right when the stress is applied, we do have some instantaneous elastic deformation. And then the strain continues to increase in time. And if the stress is held for a long enough time, then this will come to some final value up here. And so this lower strain level, we call this epsilon naught, sort of the instantaneous strain. And then this one, epsilon sub infinity, because that's where it would go if this were held for an infinite amount of time. So in other crystalline materials, the Young's modulus or elastic modulus is defined as the stress divided by the strain. And we use a similar approach here, only in this case, it's the strain as a function of time. So this modulus also actually is changing in time. And this is called the creep modulus. This isn't exactly creep deformation because it's elastic, but nonetheless, this time-dependent elastic modulus is called the creep modulus. If we hold the stress for a long time, then the creep modulus will turn into a constant, but only at a long time. Now, if at some later time, we'll call t0, we were to take the stress off, then the strain would instantaneously drop by that same amount that it went up to begin with, epsilon naught, and then it would begin to relax back down to a strain value of 0. Don't know if we can quite get it there, but it would go all the way back down to 0. We can characterize the polymer's relaxation behavior based on the amount of time that it takes for this sort of relaxation strain to be recovered. Although we don't count the time for the entire strain to be recovered, we count the time for the temperature, the time-dependent strain to reduce by 1 over E. So we're interested in this decrease here, so leaving behind a factor of 1 over E down to that point, and then we take the time from when the stress was released until the strain reaches this value, and this is called tau RET for the retardation time. So this is a measure of sort of how this relaxation process occurs. And of course, this behavior is going to be not only time dependent, but very temperature dependent as well. So we just talked about how deformation looks under constant stress. It's also possible to test polymers where the strain is what is held constant. So let's look briefly at how that works. So if instead what we have done is that we have fixed the strain, then the specimen will experience an initial level of stress, and that stress level, instead of increasing in time like the strain did, will actually relax or decrease in time. And in analogy to the creep modulus, we can define a relaxation modulus. Whereas before we have this modulus which is equal to the stress divided by the strain, but now the stress is a function of time, and the modulus here also is a function of time. And we could similarly define the relaxation time, which characterizes the process by which that stress is relaxed. And as before, this is also a strong function of temperature. So we have looked at some of the ways in which the time-dependent elastic properties of polymers can be characterized.